This lecture is part of an online course of multivariable calculus, and I'm going to talk about line integrals. So let me start. The goal is this. On the line integral, we want to integrate a quantity over a curve in plane or in a space. So basically we want to calculate the integral of a function over a curve C. Okay, so actually the curve C is just a one-dimensional object, right? It's just because it's a curve, but it lives in R3. So we can also say that it is like the single integral, the usual single integral that we already know from the single variable calculus. And it is like that, but the difference is that here we take the integral of a function of two variables. So if we just discuss the line integral in the plane, we have a function of two variables. Let me start by two variables, the s, and the function f is any two variable function whose domain includes the curve C. So one more time, C is just it is like one-dimensional object because we can parameterize it using just one parameter. Okay, so now let me just graph what we want to do. In 3D, we have x-axis, y-axis, and then z-axis. Actually, let me move this one on the other side. And we have a function of two variables, like, for example, this function f, and then we just have a curve like this, the curve C. Okay, that lives in R3. Then by calculating the integral of f over C, basically we are calculating the area under the function that is above the curve C. Just this two-dimensional object, just calculating this area. Okay, so now how to calculate that? How to compute the integral. We are just studying f of x and y over the curve C. Well, as before, we are given what? We are given a function f of x and y, and we are given a curve C. Okay, we want to sum values of f along the curve C with respect to the arc length. Okay, so let me just basically explain what we have. Just assume that we have the curve C in the plane. Everything would be similar for a curve C in the space, but let me start by the curve C in the plane. So I'm gonna graph it. Okay, this is x-axis, this is y-axis. I don't know why I graph it on the left hand side and then I move it, but let's move it to the right hand side, and then assume that this is the curve C. Okay, this is the curve C. As always, when we want to take the integral over some region, we need to partition a region. So what we need to do is to partition C into small pieces. So we are going to partition C into small subintervals. Okay, like this. Gonna do it into small subintervals that instead of being like a curve, they are like lines, right? Okay, and then I'm gonna say that we actually to compute the integral, we need a good description of C. We need a good description of the curve C, and the good description, I mean parametric equation of C. Parametric equation of C. Okay, so we need that. So I'm gonna say that I'm gonna parameterize the curve C by x of t and y of t, okay, where t is between some t1 and t2. So starting at t1 and it goes to t2, for example. Okay, so when we have the good description, when we have the actually parametric equation of C, in that case we can integrate the integral of dt from t1 to t2, right? So the integral would be easier after that, after we parameterize it, okay? So now that we partition C into small pieces, we just look at one piece, okay? So let me just basically zoom in. I'm gonna look at this piece in here, and let me zoom in. This is the part of the curve C, and this is just this part. The first point would be, for example, x of ti, y of ti, and this point would be x of ti plus 1, y of ti plus 1. Then this vector that I have in here has the equations delta xi and delta yi, for example. So if I call it dsi, this vector is dsi, the length of it would be square root of delta xi squared plus delta yi squared. So let me write this somewhere. The length of delta si would be square root of delta xi squared plus delta yi squared. If you remember, this is the formula for speed, right? So I'm gonna say that after this step, I'm gonna pick a point, pick a sample point in each subinterval, and then I'm gonna define the integral like that. It's gonna be the integral of f of x and y delta s over c would be the limit of what? I'm gonna find, so you see, basically if I go back to this shape in here, I have some small intervals like that, and then giving the height, I'm just gonna pick a point in here, and then f of that point would be the height of my rectangle times the length of delta si, okay? So I'm gonna multiply f of the sample point, yi, and then I'm gonna multiply it by delta si, the length of this vector in here, and then I'm gonna sum over all of them, and then I'm gonna take the limit so that I have very, very small subintervals, okay? So that's the definition of the line integral of a function f with respect to the arc length over the curve C. Now for actually computing this, what we need to do is to use the formula for speed. So let me basically summarize what we did, and then we can go over one example. So we're gonna take the integral of f of x and y ds over the curve C. The first step is to write parametric equation for C. So I can use x of t, y of t. The second step is to, don't forget to find bounds for parameter t. Don't forget to find bounds for parameter t, because we need to know from where to where we should take the integral. The third step is to plug in your parameterization into the function f. Okay, so plug your parameterization, actually it's better to say parameterization of C, parameterization of C into f. Well, how do we do that? We're gonna say that we have f of x of t, the parameterization for C, and then y of t, right? Then we need to find ds. Okay, what is ds? If you remember the formula for the arc length, okay, ds was the length of the velocity vector, okay, which is what? Which is dx dt square plus dy dt square, right? That's the formula for arc length. We're gonna use this formula for arc length and here, and then the last step is to basically integrate. So we have what? We have the integral of f of x and y ds over the curve C is basically the integral from t1 to t2, the bounds for t, and then f of x of t, x of t, and then y of t. And when I plug in my parameterization into f, it's just basically I get a function of t. So after that, I have a function of t, okay, and then ds, for ds I'm gonna say that I'm gonna use this formula for the speed, which is dx dt square plus dy dt square inside the square root, and now everything is in terms of t, so I can take the integral with respect to t. Okay, very good. So let me give you just one visualization of what we have. Okay, so just assume that we have the curve C. This is the curve C, and then this integral is gonna compute the area. Just assume that, for example, this part is here would be f of C. This is just the part of the function f that is over the curve C, and then we're just basically calculating this area, okay, the area that is bounded on top by the function f and on the bottom by the curve c. Okay, so let's solve one example. The example is this. Evaluate the integral of 2 plus y squared x ds over the curve c, where c is the upper half of the unit circle. So let me graph the region of my integration, which is the upper half of the unit circle, x-axis, y-axis, and okay, there you go. And the first step for solving the line integral is to parameterize the curve. So I have the unit circle. As you know, the parameterization for the unit circle would be cosine t, and then y is sine t. And it's just because it's going to start at 0 and it goes up to here, which would be the angle pi. I'm going to say that the parameters are from 0 to pi. And then you can check. Just plug in the time 0. Plug it in there. You get cosine 0, which is 1, sine 0, which is 0. So I get a 1 and 0, which is this point. Okay? And then you can plug in pi over 2. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so we get the point 0, 1. So at pi over 2 we are here, and at pi we are here if you just plug in the parameter pi into the equations, and then you get the points. Okay, so I have the integral from 0 to pi. Now let's put the parameterization into my integrand. So I get 2 plus y is sine t squared, and then x is cosine t. And then for ds, I need to use the formula for speed. Okay, so the speed is what? Let me remind you the formula. dx dt squared plus dy dt squared inside the square root. So I get what? dx dt derivative in here, dx dt would be negative sine t. So negative sine t squared dy dt. So when I have sine t, derivative would be cosine t. So cosine of t squared. So as you see here, I get sine squared plus cosine squared, which is 1. So square root of 1 is 1. So ds would be the speed times dt, which is 1 dt, right? So now let's take the integral. I have the integral of 2 dt from 0 to pi, and I have the integral of sine squared cosine t dt from 0 to pi. Okay, the first integral would be 2t from 0 to pi, and for the second integral I need to use u sub. U is sine t, du would be cosine t, right? dt actually. And so my integral would be from, I don't write the bounds, I don't change the bounds, and then after that, after I plug in u back into my equation, I'm going to write the bounds. So I have u squared du. So the first one would be 2 pi minus 0. And for this one, I have u cubed over 3. So this is 2 pi plus u is sine t cubed over 3. Now let's write the bounds from 0 to pi. Okay, so I get 1/3 sine of pi is 0 minus sine of 0 is 0. Okay, so this part would be, the whole thing would be 0, so the answer would be 2 pi. Okay, this is the area that is bounded below by this curve and above over basically the projection of the curve into this function.